Hello everyone and welcome to a new video. Today I want to talk about something which we keep hearing very often in our IT projects and that is Kafka. This video would give a very high level understanding of Kafka so that as a business analyst, product owner or tester, you feel confident and able to connect the dots when you face Kafka in your projects. Kafka is nothing but a platform that helps systems communicate with each other in real time. Think of today's world. When you make a payment, or you book a cab, or you place an order online, or receive an OTP, or even get a fraud alert from your bank, many systems are working behind the scenes. So these systems need to exchange data quickly, reliably, and at scale. And that is where this Kafka basically comes to the picture. In this session, we will understand Kafka at very high level without going too deep into its technicality. We will use simple examples from banking, payments, e-commerce, notification systems, enterprise application, and by the end of this video, I hope you should be able to confidently explain what Kafka is, why companies use it, and what its main components. So before we define Kafka, let us understand the problem, that why do we need Kafka and what does it serve. So in traditional system communication, one system directly talks to other system. For example, system A will talk to system B, system B will call system C, system C will call system D, and so on. Now, this looks simple when there are only two or three systems, but in a large bank or large enterprise, there may be hundreds of systems communicating with each other. Now, one system may need to send the same information to many other systems. For example, when a payment is made, the payment information may be needed by your fraud monitoring system, core banking system, notification system, reporting system, the audit system, the reconciliation system, and so on. Now, imagine if a payment system directly calls all those systems one by one, and if one system is down, the whole process may slow down or fail. This is called tight coupling, where one system becomes dependent on another system. Second problem is the scaling issues. If tomorrow we add one more system, maybe a new analytics system, we may need to change the existing application. Third problem is data duplication. The same data is sent again and again to multiple systems. Then, fourth problem is lack of real-time processing. Many traditional systems work in batches. That means data may move after a few minutes, hours, or at the end of the day. Kafka solves these four main problems by acting like a central highway. Um, Systems publish data to Kafka, and whoever needs that data can read it independently from Kafka. So Kafka helps systems communicate in real time without becoming tightly dependent on each other. Now let's understand Kafka using a simple analogy or simple example. The first analogy is a newspaper. Now a newspaper company prints one newspaper edition. Once printed, thousands or lakhs of readers can read it. The newspaper company does not print a separate newspaper for every reader. It publishes once. It publishes once, and many people consume it. Kafka works in a very similar way. One system publishes an event once. Many other system can read that same event independently. Another analogy or another example is we can take is radio broadcasting. So in radio station, um, the jockey, the one who plays a song or radio station basically plays a song or announcement once, and many listeners receive it. The radio station does not personally call each listener and say, "Hello, sir, please listen to the song." Kafka follows the same idea: publish once, consume many times. Again, the third example we can take is railway station, or the announcement we hear in railway station. The station announces that a train is arriving, so different passengers hear it and act according to their needs. For example, some may go to platform number two. Some may check their bags. Some may call their family. So once the announcement is the same, but every passenger uses it differently. Similarly, in Kafka, one payment event may be used by, fraud detection, notification, audit, reporting, reconciliation systems, etc. So, in short, Kafka allows one system to publish information once, and many systems can consume it independently. Now, let us define Kafka properly. So basically, when we say Kafka, we will also read it as Apache Kafka. Apache Kafka is an open source distributed event streaming platform governed by Apache Software uh, Foundation. And when we see these words, open source, distributed, event streaming platform, this sounds very technical, right? Let's break it down. So when we say open source, it means it is freely available. It means it is freely available and maintained by a large community. When we say distributed, it means it does not depend on, does not depend on one server. It can run across multiple servers, which makes it scalable and reliable. When we say event streaming platform, it means it helps capture, store, process, and distribute events in real time. So, in simple terms, Kafka is like a real time data pipeline. Kafka is like real time data pipeline. So, it can do four major things. It can publish events, that means systems can send data to Kafka. It can store events, that means Kafka does not simply pass data and forget it immediately. It can retain the events for a configured period. It can process events. That means Kafka can support real-time transformation and processing of data. It can consume events. Um, it means the other systems can read data from Kafka whenever they need it. So Kafka was actually originally built at LinkedIn and later became very popular across large enterprises. Today, Kafka is used in banking, fintech, e-commerce, telecom, healthcare, insurance, and whatnot. So, in simple words, Kafka is a platform that helps application exchange real-time data at a enterprise scale. Now, Kafka is built around one very important concept that is called event. So, an event simply means that something has happened. For example, in banking, a payment was initiated. That's an event. An ATM, somebody withdraws from an ATM, or ATM withdrawal is an event. A card transaction got declined. That's an event. Um, Customer check the balance. That's an event. All these are event. Then in e-commerce, if we come to e-commerce, once an order is placed, that becomes an event. Once an item is added to cart, that is also treated as an event. A shipment is dispatched, that is an event. Again, in CRM also we see customer register, that's an event. Mobile number update, that's an event. KYC complete, that's an event. So these are all. Anything that happens is an event. An event is not complicated. It's just the fact that something that happened in a system. Usually, an event contains a few important parts like key, value, timestamp, and header. The key tells us who or what the event is related to. For example, customer ID, account number, transaction ID, or order ID can be the key. The value contains the actual data. For example, amount, date, channel, merchant, payment status, or customer details. Then we have timestamp. Timestamp tells us what when the event has happened. It gives us a time of that particular event happening. Then we have headers or metadata. This provides additional information. So whenever we hear Kafka, people saying whenever we hear Kafka people saying event, just remember an event means something that has happened, and Kafka helps capture and distribute this information. Now let us meet the main characters in the Kafka world. Uh, think of Kafka like a movie, and every character in a movie has a role. The first character in Kafka is producer. So producer sends event to the Kafka. Second is topic. Topic is the category or channel where events are stored. Third is the broker, and a broker is the Kafka server actually that stores and serves the events. Fourth is cluster. Cluster is a group of Kafka brokers working together. Fifth is consumer. Consumer reads events from Kafka. Then the sixth is our consumer group. Consumer group is a team of consumers. Is a team of consumers sharing the work. Seventh is partition. Partition basically divides a topic. Partition basically divides a topic into smaller parts so that Kafka can process data in parallel. The eighth character is the offset. Offset basically remembers how far a consumer has read. At first, this terms producer, topic, broker, cluster, etc. may sound technical, but don't worry. We will understand each one with real life use cases in the upcoming slides. Once these eight concepts are clear, Kafka architecture becomes much easier to understand. Now let us start with the producer. So, what is a producer? A producer is any application or system that sends events to Kafka. For example, in a banking scenario, when a customer makes a payment, using a mobile banking app, the mobile banking app can act as a producer. It creates a payment event and sends it to Kafka. Similarly, when you withdraw money from ATM, ATM machine can produce withdrawal events. E-commerce application in, for example, in Amazon or Flipkart, once you order there, that application can produce order events. In CRM system, it can produce customer update events. Then in IoT sensor can produce device status events. So the producer's job is simple. It says something has happened, and I am publishing this information to Kafka and publish to Kafka. This is very similar to our news reporter. If some incident has happened somewhere, they will run there and publish it in news. The producer does not need to know who will read the event letter. So in traditional system, the sender often needs to know the receiver, but in Kafka, the producer only sends the events to a topic. It does not care whether one system reads it or thousand system reads it. So this creates a loose coupling. Um, so just remember that producer means sender, and it publishes events to Kafka. Now let us understand the topic. So what's a topic? A topic is a named category. A topic is a named category or channel where events are basically stored. Think of a topic like a folder. If you have payment related events, if you have you may store them in a, topic called payment events. Then if you have fraud related events, you may store them in a topic called fraud alerts. If you have customer profile changes, you may store them in a topic called customer updates, etc. So another analogy is a TV channel. So if you want news, you watch a news channel. If you want sports, you watch a sports channel. So that's very much like a topic. So similarly, um, consumers subscribe to the topic that contains the events they are interested in. For example, the fraud detection system may subscribe to your payment event. The notification system may also subscribe to the payment event. The reporting system may also subscribe to payment event. So all these systems can read the same event from the same topic for different purposes. So in short, topic means a name, stream, or a category of events. Producers write the events to topics, and consumers read from the topics. Now let us understand broker and cluster. So a broker is nothing but a Kafka server. So its job is to receive events from producers and store events in topics and partitions and serve them to consumers. So when a consumer wants to read an event, uh, the broker the broker is the one who provides it. In real life application, we do not depend on only one server, because if one server goes down, everything stops. That is why Kafka uses a cluster. A cluster is a group of Kafka brokers working together. For example, a Kafka cluster may have three brokers, five brokers, or 10 brokers, or even more, depending on the scale. Why do we need multiple brokers? First is because of high availability. So if one broker goes down, others can continue. Second reason is scalability. More broker means Kafka can handle many more events. Third is replication. Sorry, third is third is data replication. So Kafka can basically replicate data across brokers, so that data is not lost if one broker fails. This is also called fault tolerance. This is especially important in banking and payments, where downtime is not acceptable. So remember, broker means Kafka server, and cluster means multiple Kafka servers working together. Now let us understand consumer. A consumer is any system or application that reads events from Kafka. For example, imagine a customer makes a payment. Okay, a customer makes a payment. That payment event is published to a Kafka topic called payment events. Now, multiple system may read that same event. The fraud detection system may reads it to check suspicious activity. The notification system reads it to send SMS or email. The ledger system reads it to post accounting entries. The reporting system reads it for dashboards. The audit system reads it for compliance records. The important point is, all these consumers, so these are basically consumers, all these consumers can read the same event independently. The fraud system does not need to wait for the notification system. The notification system does not need to wait for the accounting or ledger system or the reporting system. So each consumer read at its own pace. This is one of Kafka's biggest strengths. So consumer basically means reader, and it subscribes to Kafka topics. By subscribing Kafka topic, it reads the events. Now comes one of the most important Kafka concepts: partition. A topic can be divided into multiple. A topic can be divided into multiple partitions. Think of partitions like a like lanes on highway. If there is only one lane, all vehicles will move in the same lane, and that way traffic becomes very slow. But if there are three or four lanes, many vehicles can move in parallel. So Kafka uses the same idea. If a topic receives a huge number of events, Kafka can divide those events across multiple platforms. For example, a topic called payment events have partition 0, partition 1, and partition 2. Messages are distributed across these platforms, across these partitions. This helps Kafka process data faster because different consumers read from different partitions in parallel. Partitions also help in scaling. One important point is Kafka maintains order within a partition. That means messages inside partition 0 are ordered, messages inside partition 1 are ordered, but ordering across different partitions is not guaranteed globally. Uh, for business analysts and testers, this is important because ordering requirements must be clearly understood. For example, if transaction sequence matters for an account, we may need to choose the right key or um, the right ID so that related messages go to the same partition. If if the message starts going to partition 1, um, the message and the further messages coming in a sequence should also go to partition 1. So partition means a topic is divided into multiple parallel lanes for speed, scale, and ordering within each lane. Now let us understand offset. Offset is nothing but Kafka's bookmark. Let me explain using example of Netflix. So when you watch a movie in Netflix and stop after say 35-40 minutes, Netflix remembers where you have stopped. Next time it says continue watching from the same point. So Kafka offset works similarly. Each message inside a partition each message inside a partition gets a sequence number. For example, these are the sequence number. This number is called the offset. For example, messages may have offset 0, 1, 2, 3, 4, 5, and so on. When a customer when a consumer reads messages, it keeps track of the last offset it has processed. If the consumer stops or crashes or restarts, it can continue from the last committed offset. This makes Kafka very reliable. For example, if the fraud detection system process payments up to offset 2, and then the application restarted, it can resume from offset 3. It does not need to start from the beginning unless we intentionally configure that way. So this is also useful for replaying data. If you want to reprocess old events, Kafka can uh, allow consumers to go back to earlier offsets depending on the retention settings. So offset basically tells Kafka where consumer is in the message stream. It is like reading bookmark. Now let us understand the consumer group. A consumer group is a group of consumers working together to read events from a topic. Think of a call center. Okay, if there are 1,000 incoming calls and only one agent, and there's only one agent, the agent will be overloaded. But if there are say 10 agents, the calls can be distributed among them. So each agent will have 100 calls now. So Kafka consumer groups work similarly. Suppose a topic has three partitions: partition 0, partition 1, partition 2. If a consumer has if a consumer group has three consumers, Kafka can assign one partition to each consumer. let's say this is consumer 1, this is consumer 2, and this is consumer 3. Consumer 1 reads partition 0, consumer 2 reads partition 1, consumer 3 reads partition 2. So this allows parallel processing. Now what happens if one consumer fails? What happens if one consumer fails? Kafka performs rebalancing. It redistributes the partition among the remaining consumers. For example, if consumer 2 fails, the partition may be assigned to consumer 1 or consumer 3. This makes the processing scalable and reliable. Within one consumer group, a partition is read by only one consumer at a time. So this prevents duplicate processing inside the same group. Consumer groups basically means a team of consumers selling the work. Now, this is one of the most important slides because it brings all the Kafka components together. Let us walk through the flow step by step. So at the top we have the producer. In our example, producer is a payment app. So payment app is producing something, some event. So the customer makes a payment. The payment app makes a payment event. This is step 1. So the producer produces a payment event. Now this event is sent to Kafka. Inside the Kafka, the event goes to a topic called payment events. Now this is step 2. But the topic is the topic is not just one simple box. Internally, the topic is divided into multiple partitions. The Kafka decides which partition the event should go to, often based on the message key. For example, if the key is account number, then all the events for the same account number may go to same partition. This helps preserve the order for that account. Now the partitions are stored inside a Kafka brokers. These are Kafka brokers. In the diagram, you can see broker 1, broker 2, broker 3. These brokers store and replicate the event data. This is important because Kafka is designed for reliability. If one broker fails, another broker may still have a copy of the data. After the event is stored in Kafka, multiple consumers can read it independently. At the bottom, we can see we have system like fraud system, notifications, ledger, reporting, and so on. The same payment event can be read by all the systems. The fraud system reads it to check whether the transaction is suspicious. The notification system reads it to send SMS or email to the customer. The ledger system reads it to post accounting entries. The reporting system may read it to update dashboards and report. So these consumers are not directly connected to the payment app. So here in case of Kafka, producers and consumers are not directly connected. The payment app does not call each system one by one. It only publishes the event to Kafka. Kafka then then allows all interested consumers to read the event independently. Another important concept here is offset tracking. So each consumer tracks how far it has read. If the notification system is slow, it can continue from its own offset. If the reporting system is down for some time, it can resume later from where it has or it stopped. So the complete flow is producer creates the event, Kafka topic receives the event, partition stores the event, broker manages the storage and replication, and consumer reads independently, and offset tracks the consumer progress. In simple line, Kafka allows one event to be published once, stored reliably, consumed by many systems independently. So this is all about this is how the Kafka message flow basically looks like. Now let's look at a simple visual simulation of Kafka using a banking payment example. So you can see this particular screen. This is a simulatory dashboard or a application to show the workflow of the Kafka. So on the left, you see the payment producer. This is a producer actually. So as you know, a producer is any system that creates and sends an event. In this example, the event is a payment transaction with the transaction ID, customer ID, amount, payment channel, and the payment status. So when I click this particular payment event button, the producer will create a JSON payment event. So currently there is no event here under this box at the bottom. So if I hit this send payment event, it will send the event in a JSON format. So this event will represent something that has happened in the banking system, such as customer making a payment through mobile banking. So that's what I'm going to do. I click on this send payment event button, and as you can see, so this is the event that is created in JSON format. So now this event moves into the center box. So what is the center box? This is the center box. So this is a topic, Kafka topic. So this topic is termed as payment events. So a Kafka topic is like a durable event stream. So it stores events. So this is the event. As you can see, it stores one event. So that different system can read them independently. Once the payment event reaches the Kafka topic, Kafka makes the same event available to multiple consumers. So as you can see on the right hand side, these are the consumers. So we have a fraud monitoring system, fraud monitoring consumer, SMS notification consumer, analytics consumer, AML monitoring consumer. So these are the consumer. Now each consumer receives a copy of the same payment event that we have sent, but each one uses it for different purposes. For example, fraud monitoring may check for suspicious activity. SMS notification may send a message to the customer. Analytics may update dashboards. ML monitoring may check compliance rules. The important Kafka concept here is that consumers work independently. Each consumer has its own consumer offset. As you can see, each consumer has its own consumer offset, and which shows how far it has processed messages in the topic. Now, just for demonstration, I will post one consumer. Okay. So when I resume the post consumer, it catches up. Okay. Just a minute. I will post one consumer. Say I'm posting SMS notification consumer. When I send another payment event, the other consumers continue processing normally, but the post consumer does not block them. I hit the send payment event again. So this is the second payment event. As you can see, Kafka keeps the event in the topic. So when I resume the post consumer, it catches up and processes its pending event. So this demonstrates one of Kafka's key strengths. So systems can consume the same stream of events at their own pace without slowing each other down. At the bottom, you can see the event log. So event log basically shows is step. The event is produced. The event is stored in Kafka topic. This particular consumer has processed this event. That particular consumer has processed this event. So you can see this details. So this is how the Kafka basically works. This is a simulatory dashboard to show you to give you a real time or real life feel of how Kafka workflow looks like. In a real life system, Kafka runs as a backend infrastructure, while producers and consumers are separate applications connected to Kafka. This slide gives us a big picture of the Kafka architecture. So on the left side, we have the producers. This could be your payment app, your ATMs, mobile banking apps, any app where you trigger an event. This producer sends event to Kafka, sends event to your Kafka. Inside the Kafka, we have Kafka cluster. The cluster contains multiple brokers. This is one broker. I mean, then inside brokers, we have topics. Um, these are the topics. Inside topics, we have partitions. Right. On the right hand side, we have the consumers. These consumers are could be any system like fraud detection system, notification system, ledger system, and so on. So Kafka here being in the middle act as the central event streaming layer between producers and consumers. The producer does not need to directly call each consumer, and consumer also does not need to directly connect with each source system or producer. Kafka becomes the central. Producer communicate with Kafka and consumer communicate with Kafka. Kafka is the central hub. This architecture is very useful in large organization because it reduces dependency, improves scalability, and supports real-time data movement. Now let us compare Kafka with traditional message queues such as your RabbitMQ or IBMMQ. Traditional queues are usually designed for point-to-point messaging. A message is placed in a queue. One consumer reads it, and usually the message is deleted for consumption. Right? There is one consumption per message. Whereas Kafka is different. Kafka retains the message for a configured period, and even after consumers read them. This means multiple customers or consumers can read the same data independently. Another big difference is replay. In traditional queues, once the message is consumed and removed, replaying all messages not possible. In Kafka, consumers can go back and replay events even if the data is still retained. This is very useful for your auditing purpose, recovery testing, reprocessing, reporting, and analytics. Traditional queues are excellent for certain use cases, especially command style processing. Kafka is more suitable for event streaming at scale. Okay, so don't think Kafka completely replaces all the queues. It depends upon the use cases. Um, so key difference is in traditional queue, message is usually consumed and removed. In traditional queue, message message is usually consumed and removed. Whereas in Kafka, event stored and can be consumed by many systems and replayed. So the events can be, the consumer can go back and replay the events if data is still retained. Now let us compare Kafka with API communication. In REST API communication, system A directly calls SMB and waits for immediate response. For example, take an example of payment system. Payment system calls fraud systems and waits for fraud approval. So this is this is a synchronous communication. If the fraud system is slow, payment system will wait. If the fraud system is down, payment system may fail or need fallback handling. So this creates tight coupling. However, Kafka works differently. Kafka is asyn- asynchronous, and it's a event driven. So system A publishes an event to Kafka, and it will move on. Then system B or system C and system D can read that event whenever they are ready. The producer does not wait for all consumers to respond. API communication is like making a phone call. You call someone and wait for them to answer. Kafka, however, is like posting an announcement on a notice board. So you post it once, whoever needs it will or can read it. Now, this does not mean Kafka replaces APIs everywhere. APIs are still very useful when the immediate request response is needed. Kafka is useful when we want real-time event distribution without tightly coupling systems. Um, in simple terms, use API when you need an immediate response. When you need an immediate response, you use API. and use Kafka when you want to publish events for multiple systems to consume independently. Now that we have uh, gone through the concepts around Kafka, let's see how Kafka works in the real world. Let's take an example of e-commerce application. So a customer clicks buy now, and this one action creates a sign of events. So first event is order placing. So the inventory system reads this event and checks whether the item is available or not. Uh, Second event is the payment process. So the payment system confirms whether payment was successful or not. Third event is stock reserve. The warehouse system reads this event and reserves this item. Fourth event is your shipment, maybe shipment dispatched or shipment created. This the logistic system reads this and starts delivery. Then one more event could be your order confirm or notification send. The customer receives SMS, email, or app notification. So without Kafka, the ordering system may need to directly call inventory system, payment system, warehouse, then your delivery notification, and so many systems, and that becomes messy. So with Kafka, the ordering system publishes the events, and all the interested systems consume the events independently. This makes the architecture cleaner, scalable, and real time. So Kafka is extremely useful in e-commerce platform where millions of users may place orders, cancel orders, make payments, and track deliveries at the same time. Now let's take one more example. Let's take an example of a banking payment flow. A customer initiates a payment from a mobile banking app. This creates a payment event, and that event is published to Kafka. Um, to Published to Kafka topic called say payment events. Now multiple systems consume the same payment event. For example, your fraud detection system check whether the transaction looks suspicious. The notification system consumes the same event um, and sends SMS or email to the customer. The ledger system consumes the event and posts the accounting entries. The audit system basically uh, stores the events for compliance investigation and so on. The important point is that all these systems are not directly dependent on the mobile banking app. The app simply publishes the event to Kafka. Kafka does the distribution of the event, and that's it. That is why Kafka is very useful in banking, payments, fraud monitoring, customer alerts, and real-time reporting. Okay, let us summarize the major benefits of Kafka. The first benefit is high throughput. Kafka can handle a very large number of events per second. Second is horizontal scalability. If data volume increases, organization can add more brokers or partitions. Third is fault tolerance. Kafka can replace data across brokers. So if one broker fails, data is not necessarily lost. Real-time processing. Kafka helps processing of data as soon as it is generated. Decoupling. Producers and consumers do not need to know each other directly. Replayability. Consumers can replay the past events if the events are still retained. Multiple consumers, many systems can consume the same event for different purposes. Then enterprise or durability. Kafka can integrate applications, databases, data tables, analytics platforms, and microservices. So the main value of Kafka is not only speed; it is speed plus the main value is not it's not the speed; it is speed plus reliability plus scalability plus flexibility. So this is in short the benefits of Kafka: speed, reliability, scalability, and flexibility. So, however, Kafka is powerful, But Kafka also has some limitations. First is Kafka is not a database. It can store events for a configured period, but it should not be treated like a permanent business database. Second is the design. If topics, partitions, keys, and schemas are poorly designed, Kafka can become difficult, very difficult to manage. For example, if we choose the wrong key, related events may go to different partitions, and ordering may become a problematic case. Kafka requires monitoring strictly. Teams need to monitor broker health, consumer lag, topic size, disk uses, replication, and failures. Kafka has your operational complexity. Running Kafka at enterprise scale requires skilled teams. Messaging or message ordering needs careful handling. Kafka guarantees ordering within a partition, um, not across all partitions globally. And Kafka is not always required. Like for small applications or simple request response scenario, API or traditional queues may be enough. So Kafka is very powerful, but when used for right problem, but it needs careful architecture and governance. Let us understand Kafka in microservices architecture, how it looks like without Kafka and with Kafka. Without Kafka, microservices may directly call each other. For example, service A will call service B will call service C, then service D. This creates a chain of services. So if one service fail, the whole chain gets affected. Also, if we want to add a new service, we may need to change in the existing services. So this creates your tight coupling. And with Kafka, services communicate through events. Basically, they communicate through events. For example, the order service publishes an order created event. The inventory services consumes it. Payment service consumes it. Notification service consumes it, so on. So this makes systems more flexible. If tomorrow we add a recommendation service also, it can simply consume the same events without changing the order service. That is why Kafka is very popular in microservices based architecture. It helps services remain independent while sharing real-time data. Now, Kafka is also widely used as a data pipeline hub. In large organization, data comes from many source systems, right? Core banking system, CRM platform, mobile app logs, ATM networks, third-party APIs, payment gateways, card system, and so on. All these systems produce data. Kafka can act as a central highway where this data will flow. Then Kafka can send this data to different destinations. For example, database for operational storage, a data lake for big data analytics, a warehouse for reporting, a fraud engine for risk monitoring, and so on. That is why Kafka is also called as data pipeline hub. So Kafka Connect is commonly used to connect Kafka with databases, applications, and analytics system. In enterprise architecture, Kafka often sits in the middle as a real-time data movement layer. For business analysts, uh, this is important because Kafka often appears in integration requirements, data mapping, event design, system flows, and non-functional requirements. And with this, we come to the end of this video. Hope this video enlightens you on the concepts related to Kafka. If you found this video really helpful, do give a like, hit the subscribe button, and share it with your friends or other learners. We will meet in the next new video. Thanks for watching. Bye. Happy learning.